One, two, three. Okay, hello, good morning, good evening, good afternoon, everybody, wherever you might be. Well, we happen to be in Trieste, so maybe I should say buongiorno, buon pomeriggio, and so on and so forth. Ciao a tutti, buonasera. See, this is truly hybrid right now because it's a unique occasion when three organizers are in the same room, Ludwig, Francesco, and I. And we are really very happy that this is our way of going out of the pandemic. So we enjoy having you guys on Zoom, but right in the room, we have 2, 4, 5, 7 people in the room, okay? So without any further ado, I introduce Francesco D'Andrea from Napoli, and he will tell us everything and more about the convolution algebra of a tolerance relations.
Okay.
Francesco, the floor is yours. Take it away.
Thank you, Piotr. Okay, so let me start with some references, because this talk is based on a joint paper with Gianni Langhi and Fedele Lizzi. The first one,
Gianni is in the office,
which is here, and yeah, this is the first one that you see in this list. This is a recent paper, but you can see other references, because I would like to tell you a little bit in a few minutes why we started working on this before even telling you what this is about. So at least for me, we started interesting about this in 2013, between 2013 and 2014, when we wrote with Fedele and Pier Martinetti a paper about spectral geometry with a cutoff. So what was the idea in this paper? Very quickly. So it is well known to everybody doing non-commutative geometry that if you look at the, at least in the example of an oriented Riemannian manifold, you have your D plus D star, that is your Dirac operator in this case, so the exterior differential plus suitable adjoint. And so whenever you have a Dirac operator, for example, on oriented Riemannian manifold, all the metric information, so the information about the Riemannian metric are encoded in D. And in particular, so D tells you about the metric on the manifold. And if you look at the spectrum of the Dirac operator, suppose, the manifold is compact, so this will be made of eigenvalues. And if you look at larger and larger eigenvalues, they tell you about what's happening at short distances in some sense. So you can see this from different point of views. For example, if you're interested in the metric on state space induced by a Dirac operator, when you have, for example, a spectral triple, one way to see that the tail of the spectrum of Dirac operator tells you something about short distances is this kind of equality that you probably have seen many times, even already in Convook, I think. Saying that the Dirac operator is some kind of inverse of the line elements. So if you take large eigenvalues, this means that you're looking at very short distance. So now the idea is then you have a spectral triple, for example, the one associated to a Riemannian manifold. So what happens if we cut the spectrum of the Dirac operator? So we introduce, like physicists do, a cutoff, which can be implemented, for example, by a projection on the Hilbert space where the Dirac operator acts. So you truncate the Hilbert space in such a way that you don't see large eigenvalues. You only see the eigenvalues that in absolute value are less than lambda. And since, because of what we just said, if you cut the tail of the spectrum, well, you should not see short distances anymore. So some kind of minimal length should appear. And this was the spirit, behind this paper. We tried to see if in the framework of, at that time, we were working with compact quantum metric spaces. So an order unit space plus a semi-norm coming in particular from a Dirac operator. And then we were studying metrics on these state spaces and seeing what happens to these distances when you introduce this kind of cutoff. If in some sense there is a minimal length appearing or not. And this was, the interest was, for example, in physics, this is interesting because if you have a minimal length, you may think of avoiding the singularities, like, I don't know, black holes in general relativity, things like that. Okay, this was almost 10 years ago. And then there was this paper, maybe, sorry, first I show you which paper. There was a recent paper, I mean, 2 years ago, by Kohn and Van Zuilecom, again about the spectral truncations, where they continued with this idea that if you truncate the Dirac operator, you can obtain some kind of coarse-grained approximation of your geometric space, which is what you expect, for example, when you have instruments with a finite resolution. You cannot see, for example, arbitrary small distances. And what they do in this paper is that they introduce a new framework, and this new framework is operator systems. So instead of, when you truncate a spectral triple, you don't have an algebra anymore. But you have something, instead of having an algebra dense in a C-star algebra, when you truncate, you have something which is dense in an operator system. And then, for example, here they introduced the notion of operator system spectral triple, where the algebra is replaced by this more general notion. In particular, there was a very nice comment about how these operator systems can come from tolerance relations. So a tolerance relation, I can tell you immediately, we will see in detail in the next slide, but this is basically an equivalence relation minus transitivity. You forget about transitivity, and this is a tolerance relation.
Francesco, if I might just drop in for a second. You see this bottom paper of Mark Riffel, so he will give a talk about this paper on Thursday.
Yeah, I know. This is why. Yes. So last reference was another paper by Walter, which is no longer there. So I apologize with Walter if he's online listening. And it was replaced by the more recent paper by Riffel, but I will tell you in a moment. Okay, so there was this nice comment in this paper from Kohn and Walter that if you forget about transitivity of an equivalence relation, from an equivalence relation you can construct a groupoid and then an associative algebra, the convolution algebra, and associativity of the algebra comes from transitivity of the relation. So you don't have this if you don't have transitivity, but what you can construct is an operator system, which is a very nice framework, because still you have you can talk about the state spaces. It's very, I mean, it's a very rich theory. Okay, so then what happened is that me, Gianni, and Fedele, we were, I think, in Trieste probably. I'm not sure when we started talking about this, but we saw that Kohn was interested in this topic. And okay, so we said, okay, maybe it is interesting. Maybe we should keep working on it after almost 10 years. And so what we did was, so in Kohn paper, in Kohn and Walter paper, they talked about operator systems that they don't have a product. And okay, it is true that if you don't have transitivity, you can construct a product that is no longer associative. So from some point of view, it's less interesting, but we thought, okay, maybe we can still study this product and see if we can say something about it. And this paper that I'm talking about today, this is about this product, is how to associate a convolution algebra to a relation that is not transitive. And this is, you just imitate the case of equivalence relation. Is not something really, I mean, there is a naive way to do it. And then we study the properties of this product. And I will tell you about this in this talk. Okay, then yes, so here we pass from tolerance relation to non-associative algebras. There is another paper by Kohn and Van Zuilecom that was basically appeared 1 month before our paper, where they pass from tolerance relation to operator system. So they realized that this program that they started suggesting in the previous paper. In particular, they focus on proximity relations, and I will tell you what these are in the next slide. Okay, these are a few references, but there are many more. I mean, after this paper of Kohn 2 years ago, there was really a lot of activity, both on operator systems and also on truncations of spectral triples or truncations of compact quantum matrix spaces and so on. And the most recent paper that appeared on Archive a few days ago is the one by Mark, where he really talks about the truncations of, well, this is compact quantum groups, and then he studies convergence in the sense of quantum metric spaces. So in his Gromov-Hausdorff distance. Okay, yeah, I think Marco will talk about this in November.
23rd of November, this will be a Thanksgiving talk.
Okay, so he will tell you about this. Okay, now, so let's see the details. So I start from the beginning, from the definition of tolerance relation. Suppose you have a set S, then a tolerance relation is a relation on S which is reflexive and symmetric. This means that every element of S is in relation with itself, and if A is in relation with B, then B is in relation with A. Okay, so you are reflexive and symmetric, not necessarily transitive. How can you visualize a tolerance relation? Well, since R, this subset of S cross S, which is here, since it contains the diagonal, you can just remove the diagonal from R. It is not a big damage. You can always add the diagonal back and you get R. And if you remove the diagonal and you think of elements of S as vertices and the elements of R minus the diagonal as edges, then you have a simple graph, meaning that, well, maybe you want to define a simple graph only in the case where S is countable or even finite. Here, S is not yet finite. But okay, say at least in the countable case, this is what you can call a simple graph, meaning that you removed all the loops because I killed the diagonal, and what remains is that two edges, two vertices are connected by an edge if and only if they are in relation.
Sorry, by a loop here I mean loop of length 1, right?
Yes, so yeah, usually called cycle a loop of length, arbitrary length. So loop is always of length 1 for me. Yeah. So there are no loops because I removed the diagonal. There are no multiple edges, of course, and it is undirected because you have symmetry. Yeah. Okay, so basically a tolerance relation, at least if S is a good set, I don't know, countable is, then this is the same as a simple graph. The easiest example, easiest non-trivial, so easiest example of a tolerance relation which is not an equivalence relation, well, to have for such an example, you need at least 3 elements. So here S has 3 elements, X, Y, and zeta. X is in relation with Y is in relation with zeta, and X is not in relation with zeta. So this is not transitive, but you have the other 2 properties, and it's fine. This is a very simple example, but we will use actually this example to say something about arbitrary finite dimensional convolution algebras, let's say.
So just a stupid question, why do you call it tolerance relation?
So this is, I mean, we learned about this in Alain and Walter paper. So they used this name, and there is already in that paper, there is a reference. So we simply checked these references to learn a little bit about this thing. I think I would say that it's something that is not studied not really by mathematicians, but engineers. Is more applied. I think it was neuroscience. You remember? Yeah.
Student of Zeman actually invented this name.
Yeah.
So, but also topologists.
Yeah, yeah, I think Zeman is the one who introduced the name. Maybe even in his thesis, I'm not sure. Then somebody else formalized everything, and this name remains. Okay, so what are examples of tolerance, non-trivial examples of tolerance relations, and possibly from real life? So examples that you can see in around you, let's say. Okay, the first example is causality and special relativity. You can take S, the set R to the power 4, so quadruples of real numbers. Here I write 1 for matrice, so physicist notation to say that I consider the metric with the signature plus, minus, minus, minus. And two quadrivectors are in relation if and only if they are, the difference is either like or time-like, meaning that so A is in relation, small a is in relation with small b, if one is in the light cone of the other. Okay, in this picture you can see 3 points in Minkowski space, x, y, and zeta. X and zeta are both in the causal future of y, so they are in relation with y, but their light cones, they don't intersect. So x is not in relation with zeta, and zeta is not in relation with x. Okay, and if you forget that you have infinitely many points, because this is R4, if you forget about this and really focus only on the picture, you see that this is the same picture that we had before. So 3 points, and okay. One is in relation with both, and the other two are not in relation to each other.
And it's clear that you have a symmetry, right? So y is in the cone of x and y.
Yeah, because you have a double cone, even if I don't.
So future or past, yes.
Yeah. Yeah. Okay. So the second real life example is from Wolfram Mathematica, but I'm sure that any other mathematical program will work. So in Mathematica, you can do the following. I should say that we found this on a math blog, which is a very good source of curiosities and anecdotes. So in this math blog, there was really this example of a real life example of a relation which is not transitive. Actually, the question that somebody asked in this blog was, is there a framework where equality is not transitive? And in Mathematica, equality is not a transitive relation. So what you do is you define 3 real numbers as follows. Well, x can be anything, but here I put x equal to 1. It could be 0 or any other integers, for example. Then here epsilon is a very small constant, and to make it work, for example, you can choose 50 times some constant that is defined inside this program, which is called machine epsilon. Then you define y as x plus epsilon, z as y plus epsilon. And if you ask Mathematica which of these 3 are equal to each other, Mathematica will answer that x and y are equal, that y and z are equal. So they are too close to each other for Mathematica to distinguish these 2 numbers. But x and zeta, they are not equal. 2 epsilon is big enough that Mathematica understands that these are not equal. So this is related, of course, to the finest capacity of a computer to store information, so numbers, for example, real numbers. But this is what you would expect also in real life if you perform an experiment with an instrument that has, as usual in real life, has finite resolution. Okay. So next, the next example is what somebody call proximity relations. So what is a proximity relation? You have a metric space. S is the set and D is the distance. And you fix epsilon greater than 0. And you define the relation as follows. You say that A is in relation with B if and only if their distance is less than epsilon. So this is what we call a proximity relation, is an example of a tolerance relation. Sometimes it's even transitive, usually is not. And in the simplest example, take the real line with the normal distance, then it is not transitive. But in other cases, it can be transitive. So for example, if D is an ultrametric, then you get a transitive. And I should say that the example number 2, equality in Wolfram Mathematica, this is a special case of this third class of examples. You have also in that case, you have an epsilon and some kind of distance. Okay, example number 4 is when you have a covering U of a set S, any covering of any set, you don't need a topology here yet. And then you can define the tolerance relation as follows. For an equivalence relation, what you would do, given a covering, you would say that 2 points in S are equivalent if you cannot distinguish them, if they cannot be separated by sets in the covering. For a tolerance relation, so for the equivalence relation, what you see here, you just replace existence by for all. That is, if here you put for all, you get an equivalence relation associated to the covering. With existence, you get a tolerance relation. So X and Y are in relation if there is at least one set in the covering that contains both. So why this is interesting? Well, first of all, because proximity relations are a special case. Not always, but for many metric spaces, you need something called the midpoint property. I'm not going into the details, but if you think a little bit about it, you will understand why you need this property, which is that you have for many metric spaces. And for example, you have for the state space of C-star algebra with distance induced by a leap semi-norm, so quantum metric spaces and so on.
Hey, Francesco, can I stop you for a second? Chiara, if I remember correctly, when we use exactly this quantifier for all, this is like it was in our project we were working on, right? And when it's really this equivalence relation, this is how we get to these flabby sheaves and so on and so forth. Okay, okay. Yeah, this.
And okay, yeah. So if you take a metric space and you consider a covering with balls of radius epsilon half, then you get a proximity relation with parameter epsilon. And this midpoint property is just to show that there exists a center of this ball. I mean, you can check, it's not very complicated. So another reason why this is interesting is that, for example, with for all instead of existence, so with equivalence relation instead of tolerance relation, this construction was used by Sorkin in his series of works on approximation of topological spaces with finite posets. Okay, so we were wondering at some point if we can do something similar with a tolerance relation, and the answer is that we don't know yet. But okay, that is a topic for another topic. We get some answer. So there is one more class of example, which is the tolerance relation associated to actions, but this is postponed to after I tell you what is the convolution algebra. So we will see what is this class of example later. Okay, so now we have to add topology a little bit, but not much. So X is a topological space. R is a tolerance relation on X. I assume that there is a topology on R, which is not necessarily the one induced by the product topology on two copies of X. And actually, usually it will not be. And inspired by the example of equivalence relation and associated groupoid, we will say that this relation is étale if with these two given topologies, F on X and on R, the projection from R to X, so projection onto the first factor, this is a local homomorphism. This will be, depending on the convention, this will be either the source or target map in the associated groupoid. Okay, so in the transitive case, this really means this is the definition of étale groupoid, if you think of this relation as a groupoid in the standard way. If you have a relation which is étale and also Hausdorff, then you can perform the same construction that you do for groupoids. You take the space of compactly supported function on the relation on R, and you can define a product and an involution, and you get a star algebra. The only difference is that now the star algebra is not associative. So in particular, the product, you see the formula here, F star G, you have to evaluate on a pair of elements of X, of capital X, so X zeta. And the formula, here you have a sum of F, X, Y, G, Y, zeta, where Y, you take Y, you sum over all Y that are in relation both with X and with zeta. And this is a function on R. So this is, we define this only for X and zeta in relation. It's really similar to what you have for equivalence relation. And the étale condition is just because we wanted to work with sums instead of deciding what is a system of an R system for something which is not a groupoid, basically. Okay. Let me see, there is a question, maybe. Yes, so we will see many finite examples in a second. Okay. First of all, if X and R are discrete, then automatically, well, you get something which is automatically étal. And you can define, you can see what is the product in the usual vector space basis of CC of R, because now compactly supported just means finitely supported. And you can call capital E ij the delta function of the pair ij in R. So I and j are in relation. Capital E ij is the function set that on the side ij is 1 and everywhere else is 0. If you compute the product with the formula that I gave you, so this is not a definition, this is what you compute using the previous definition, and is very similar to what you already know for equivalence relation, which in the finite case means simply matrix product. So the product of two such things is you get delta jk, where j and k are the middle indices, EIL, but you get these only when I and L are in relation, and if they are not, automatically you get 0 from the definition. So this 0 is the difference from the case of equivalence relation. For equivalence relation, if I and j are in relation, this is the only case where this function is defined, and k and L are in relation, and j and k are the same, then I and L are in relation because of transitivity. So you are always in this first case automatically because of transitivity.
So this is the only difference from the equivalence? I don't remember in matrix there is this intermediate, but because there is
You just don't have 0 otherwise, you see.
Here you have zeros on top when j and k are not equal, but for an equivalence relation, you are always in the first case.
This would be matrix product.
Yes.
Yeah, the one on top, including the zeros, is the matrix product. The one in the bottom is extra zeros. So sometimes if you multiply two matrices, you wouldn't get 0, but with this product, you get 0. So X and Y are not necessarily finite, but I mean, then you can understand immediately what happens in the finite case. First of all, only in the finite case, the algebra is unital, and the unit is the sum of all EII. And okay, so if R is an equivalence relation, even in the non-finite case, still you get an associative algebra. And you can consider, as usual, the associated universal sister algebra, and you have the usual construction, maybe more than one. Maybe you have full and reduced associated sister algebras. Okay, if R is not transitive, you check immediately that with a simple example that the product is not associative. And here, okay, you cannot work with the sister algebras or anything similar. There is for non-associative algebra, there is no the notion of representation that works for every class of non-associative algebras. And so this second part, you don't have it. So still, you don't need to work with complex numbers. In the associative case, we like the complex numbers because we pass to sister algebras. Well, you can also use real sister algebras. But if your field is not R and is not C, sister algebras are not defined.
By the way, there is some way.
Yeah, so for specific classes of non-associative algebras, there is a notion, a good notion of representation. There is some, I think, some general philosophy, but I don't want to enter into these details, but you will see an example of this general philosophy later on. So here, your field could be something different from R and from C. You can work over an arbitrary field and still everything makes sense. And I will need this only on one slide. In one slide, I will talk about, real numbers. So nothing more exotic than that, instead of complex numbers. So when X is finite, so let's say X is the set 1 to n, then you can identify compactly supported function on the relation using this delta function. You can identify in the obvious way with a subset of n times n matrices. And you don't have all the matrices because EIJ are defined only when I and J are in relation. So you get an injective map sending these matrices to what you can expect, to the canonical basis of n times n matrices. You get an injection of this vector space here, which in general will not be surjective, and in any case is only a linear map. Is not, of course, the product on your convolution product is not the restriction in general of the matrix product.
So your functions are f-valued, right?
In general, they are f-valued, but they will be almost always complex valued. So really only in half slide, f will be real numbers. See, yes, so the f here is the f here.
Yeah.
So, yeah. Okay, so let us focus now on the finite dimensional case. And so now again, X is the set 1 to n. R is a tolerance relation on this set. The topology both on X and on R is the discrete one. You don't need to do anything more complicated than this. And I will need the notation also for the graph associated to the relation. So gamma is the graph that associated to R in the way that we showed at the beginning. So to get the edges, you remove the diagonal from this R. So
simple graph means no length one loops, and
no
multiple edges.
No multiple edges, no loops, and no weights on the edges, and no orientation, of course, is unoriented. Okay, so I denote by A of gamma the convolution algebra of this tolerance relation. So is A of gamma instead of A of R. I use gamma here because we will see immediately why. So this is given by, as I said, you have something which is inside n times n matrices. So you have a subset of this matrix algebra, and you put a product which is not a restriction of matrix product. Then you can take your graph and you can decompose it into connected components in the graph sense. And I denote by gamma I the general connected component. And there are a lot of properties that are not difficult to check, especially once you know what you want to prove and you have an idea of how to do it. Is not difficult. So this is one of those cases where all the proofs are simple once you know them, after you know how to prove things. So in particular, you can show that really the only case, okay, you can show that the relation is transitive if and only if each connected component of the graph is complete. This is very simple, is not complicated.
And remember, complete graph means that between every pair of vertices there's an edge.
Exactly. So this is simply because if you have a path between two vertices, so you have a chain of relations, and by transitivity you can reduce this chain to a single edge. So whenever two vertices are connected, they must be connected by a length one path. And this is transitivity of the relation.
Yeah. Okay.
Yes, then the definition from the definition of convolution product, you immediately see that your algebra, if you work with these EIJ matrices, you see that if you take two matrices that are delta functions on edges in different connected components, then the product is a zero. And this means that your algebra is really, you can decompose it as a direct sum of the algebras associated to each connected component. So in many cases, you just focus on connected graph and you deduce the general result from the connected case. Now, the simplest possible example. The simplest possible example is when n is equal to 3, and since you want a tolerance relation which is not an equivalence relation, well, this is what you get. Up to a permutation, this is the only one. Is 2 is in relation with 1 and 3, 1 is not in relation with 3. The convolution algebra of this relation, of this graph, I will denote it by A3. Now, with this A3, this is very simple, so you can have fun. This is just 3 times 3 matrices where you put two zeros, you kill two matrix elements. And with this identification with the matrices, you can check everything you want. You can prove, for example, that this algebra is not power associative, so in particular is not associative. And you have this very simple matrix with zeros and 1. You compute this matrix times itself 3 times, and you check that you don't have power associativity. Then actually this is used to prove something a bit more general. With this, you can prove that that in general, for any graph gamma, the following four properties are equivalent. A gamma is associative, is equivalent to a gamma is power associative, and of course you have to prove only one direction, only one implication. And associativity is equivalent to the following condition, point number 3. So a gamma is associative if and only if it has no subalgebra isomorphic to A3. So I remember that in the theory of Jordan algebra, there is something similar, because this A3, you have the Albert algebra that plays some kind of similar role to this A3. So it was quite funny that there is something that remembers Jordan algebra. And then the last point, this is equivalence to R being an equivalence relation. That is the only case when A gamma is associative. So associativity is really completely equivalent to transitivity of the relation.
So this A3 is like a basic building block of non-associativity,
Yeah,
non-transitivity.
like the Albert algebra for, Okay, then using this, you can, the reason why we checked these properties is that we wanted to see if some famous example of non-associative algebras could be obtained from this construction. And what the yellow statements tell you is that these interesting algebras actually are not examples. But so, for example, the first thing when you study non-associative algebras is, well, maybe let's check if octonions are in this class of examples. Now, the point is, like in the case of sister algebras, you have a lot of elements that you can multiply and you get 0, even if the two elements are not 0. You just take two orthogonal projections. Mm-hmm. And this is what you have here. The only case you get a division algebra is the trivial case when you have a relation on one point and the algebra is just the base field. So you can get real numbers, complex numbers, and that's it. In particular, you cannot get quaternions, you cannot get octonions, and you cannot even get sedenions. And for this, to prove this, you just observe that sedenions, they are not associative, but they are power associative. So they are power associative, but not associative. And since these two are equivalent for our algebras, so this means that it's not in this class of examples. So unfortunately, these are algebras that you don't have in this family of examples.
Can you remind me what sedenions are?
You build from octonions, like you build octonions from quaternions with this Cayley-Dickson construction. It's pair of octonions with this.
Okay.
Yeah.
Yeah.
Okay. So, I mean, if somebody is interested in for example, sedenions and octonions, they can be obtained as twisted group algebras. This was in a paper by Majid and Albuquerque, I think.
I mean, I remember Sean talking about anions, right?
Yeah.
And
so everything that you can get from this Cayley-Dickson construction as an interpretation in terms of twisting of a group algebra.
And they are not in your class.
And so this is something different from twisted group algebra. It's something else. So how can you construct more examples? Well, one way, how can you construct a lot of examples of groupoids and then of groupoids sister algebras? Well, for example, transformation groupoids, these are a huge class of examples. I mean, there is probably a lot of groupoids, interesting groupoids that are not transformation groupoids, but still from a group and a G space, you can construct already a huge class of examples. So given a group action alpha, so here G is the group and X is the G space, you have the relation of being on the same orbit. So 2 points are in relation if there is one can be obtained from the other acting with a group element, and this is an equivalence relation. So under a technical condition, you can prove that this is étale, and in particular, G must be discrete. This is one important condition. So this you miss a lot of interesting groups. And if X is compact, then you can prove that the completion of the convolution algebra here is not G, here is R. This is a typo. This is the compactly supported function on the equivalence relation with convolution product. and either R or the groupoid associated to this relation. And the convolution algebra, you can prove that it can be completed to get the cross product of C of X into G. So for a free and proper action, then we know a lot of things about cross products. We know that for a free and proper action, this is more equivalent to functions on the quotient space. And so the idea is that when the quotient space is not a good quotient, I mean, it's not, for example, Hausdorff, when you have a bad quotient, the cross product is what replaces continuous functions on a quotient to describe this group action. So it's some kind of non-commutative quotient space, or non-commutative analog.
I'm a bit confused, sorry. So X is all the time here compact Hausdorff?
Compact Hausdorff, yes. If the action is free and proper and G is discrete.
But group is discrete and need not be finite. Okay.
I mean, there is a theorem also in the non-discrete case, but since I gave the convolution product with a sum, because I don't know what is our system when you don't have a groupoid, then okay, let's stick with the discrete case. Then maybe in the future we can pass to the locally compact Hausdorff maybe case. Okay, so examples, but you can reduce many interesting examples to the discrete case. For if you have a foliation, you use the discrete that instead of the full groupoid, you take the reduced one, choosing a transversal, and you can pass to a discrete to an étale groupoid. So this is an example of foliations, orbifolds, even tilings of the plane. There are dynamical systems like Boston that fit into this paper. And okay, so this is very famous stuff for people doing the non-commutative geometry. I'm sure that everybody in the audience.
Sorry, first what it bothers me. So when action is free and proper, your X is compact Hausdorff, your G is discrete, when actually G must be finite.
Maybe it must be finite, yes. Yeah. Yes.
Yeah.
Yeah.
Okay.
Yeah, because we started, I mean, in general, but yes.
Okay.
Yeah.
Okay. Just sanity check.
Yeah. Okay. So, yeah, I think that actually this condition free and proper works also for locally compact. You don't need discrete, so it's the same condition, but just the statement about the convolution product that is. Okay. So why is the algebra associative, or why is the relation transitive? Well, the relation is transitive because you have a group action, which means that first of all you have a group and the product in the group is associative. And then also you have an action, meaning that if for any two group elements, G and H, if you compose alpha of G with alpha of H, this is alpha of GH. So how can you generalize this thing to get tolerance relations? But well, first of all, you can try to forget about this condition. And so you have a group, but not really an action, something a bit more general. Or you can forget about the second condition. Maybe you don't even need a group. And in the next two slides, I want first to try to motivate the first setting where you have a group, but not an action. And then try to explain what you can do in the more general possible setting. So take a unital C-star algebra, take a group G, and suppose you have a group homomorphism from G to out A. So this is what happens, for example, in this non-commutative geometry approach to the standard model of particle physics and so on, where A is almost commutative. And this is interesting because if A is almost commutative, so is functions on a manifold, tensor product with a finite dimensional C-star algebra, then out A is the group of diffeomorphism of the manifold. Maybe it's not always true. Maybe you need a full matrix algebra, right? I'm not completely sure. Now I'm thinking about it. So maybe to get a diffeomorphism, you need a full functions on M times a full matrix algebra. And let me see comments on this. I don't see comments anymore. Okay, Piotr, maybe you can tell me.
Well, this is a comment from Richard about our paper. That's irrelevant to the topic.
Okay. And
there's some private chat in the background.
So yeah, so anyway, so at least if you have a functions on a manifold, the tensor product with full matrix algebra, out A is the diffeomorphism on M, and then this means that this your group G is acting on the manifold by diffeomorphism. So now we want to lift this action. For example, this is something that you want to do when you have this in this approach to the standard model of particle physics. Maybe you want to lift the action of G. I mean, you want to lift this map to a map from G to out A. Well, this you can always.
That's what it's simple.
Yeah, I mean, it's not any finite dimensional. I think you need really full matrix algebra. Otherwise, you would have permutations, right? But maybe not. Maybe anything. We have to double check in our paper because I don't remember. But we talked about this we checked in the paper with Andre, right? Anyway, this is just a motivation. So suppose now you want to lift this to a map to out A to perform this cross product construction, but what can you do? Well, you can take any section of the projection from out to out with O that I pronounce unfortunately in the same way, but I hope you understand. You have this out that you quotient, and you can take a section of this quotient map. You compose this morphism with this section, and you get some map alpha from G to the automorphism of A. The only thing is that this will be not a group homomorphism. It will not be an action of G on A in general, but it will satisfy something close to the condition of an action. So it is an action up to the adjoint action of unitary elements of the algebra A, so up to inner automorphism. And this kind of generalized action, where you have some F that satisfying suitable conditions, this kind of action was the starting point of the construction in a paper of Bobknecht, Hannapus, and Mathai. I hope the pronunciation was okay. Was the starting point for a theory of non-associative cross products. And here a theory of cross product in the sense that they put norms complete and everything like you would like to do. Another framework where you have a group but not really an action is the following. Suppose you have a metric space XD and a map alpha still from G cross X to X, and a map which is not an action but satisfies the following condition. For some constant epsilon greater than 0, so alpha G, alpha H of X is not really equal to alpha GH of X. They are not really equal. They would be if it were an action. Here they are not equal, but they are close to each other. So their distance is less equal than this constant. So you see, here is a mix of these two ideas of proximity relation and group actions. This is what is called a quasi-action. There are people studying it in a completely different, I think, network from ours. But if somebody is interested in our paper with Gianni and Fedele, there is a reference to a paper where people study this kind of things. And so this is another possible framework where you have a group, but not really an action. But still you get, so instead of an equivalence relation, if you consider this relation of being on the same, now not really orbit, because I wouldn't call it an orbit, but I mean, this gives you still a, so not a transitive, but a nice, maybe nice tolerance relation. So what is the more general framework? Let's see really what is the minimal assumption that we need to get a tolerance relation from this kind of orbit construction. So G here now is just a set, nothing else. But on this set, I have two operations and one special element. The first operation is binary. The second is unary. So the first, you can call it multiplication, and the second, right inversion. And then there is an element that we call right unit, denoted by 1. The only condition that you impose on this data, on this collection of data, the only condition is that for any two elements in the set, G and H, if you multiply G with H and then with H minus 1, this is the same as G multiplied by 1, which is the same as G. So H and H minus 1 the product is not really 1. H minus 1 is not the inverse of H, but is the inverse if you act first with H and then with H minus 1 from the right, and putting parentheses in the correct places, because we don't assume associativity. So it would be nice to have a full name for this kind of algebraic structure. In the paper, we called it magma with red inversion and unit. In case somebody will be interested in studying this kind of stuff, maybe he will find a better name.
So here the point is that G can be taken equal to 1, but it's only a right unit. So if you write just one convolution H, it's not H, right?
1 is not the left unit.
Yeah.
Yeah, it's only right unit. Yes.
That's why there's a comment that H inverse is not really the inverse of H.
But also because no, in any case, H times H minus 1 is not 1 in general. You will see immediately an example.
Yeah, it would be 1 if you had read G's. Sorry, but 1 is two-sided inverse.
Yes, so I will show an example immediately. I just give you one more definition, and then it's a very simple example where everything works and is not a group and anything.
Okay.
Then when you have this notion of magma and so on, this kind of structure, whatever cool name we can find in the future for it, you have a natural notion of a right action. So now if X is a set, a right action is a map from X cross G to X, similar to the group multiplication, except that you have X here and here instead of G, will denoted by a triangle as usual. And the condition that must be satisfied to call it an action is the same as here, except that instead of star, I put the triangle. So it's the same kind of equation, but with triangle instead of star. So if this is satisfied, I will say that I have an action of this magma on a set X, and given such an action, you can define the canonical map in the usual way. You take the canonical map takes a pair in X cross G and gives you a pair in X cross X, and the formula is the usual one, except that you don't really have a group action. But still, let's call it canonical map.
But G is still a group, right?
No, G is not a group. G is this kind of magma.
Magma, sorry.
Yeah,
yes,
it's this kind of map. And you have this kind of action. Still, you define the canonical map in the usual way, and you call R the image of the canonical map. So first of all, this condition is what you need to get a tolerance relation. So the image of the canonical map now is a tolerance relation. I thought, okay. In a moment, you will see examples. Sorry, let me go in order. With the canonical map, you can define what you mean by free and transitive action in the obvious way. So if the action is free, if the canonical map is injective, and transitive if it is surjective. So here is really like for groups, except that you don't have a group. But you can study now examples, see what it means free, what it means transitive. So for example, G acts from the right on itself by right multiplication. So this product of G from the right satisfies the axiom of an action. And you can check that this action of G on itself is free if and only if the product is left cancellative. So it's not something completely crazy. It's yes, so this will be an example. Thanks, Paolo. Unfortunately, I put all the examples at the end of the definition, but you will see. It's not any loop, it's Mofang loops, because that is what you need to satisfy this unique axiom, but we will get there in a moment. Okay, now what you can do is you take the axiom defining G and change left with right, and you get this other equality. This other equality, if it is satisfied for every pair of elements of G, of elements in G, then what you get is that the right action of G on itself is both free and transitive. So this is the condition that you have to add to get a right action which is both free and transitive. Now, I think now we are ready for the first example, which is very simple. And so you take G, the non-zero real numbers, and the star is the division. And then you can check that now y and y minus 1, they are not one the inverse of the other for division, but still they satisfy this axiom that they should satisfy. And you get an action in particular which is both free and transitive. Another example where the action is both free and transitive are these Maufang loops. So for example, unit octonions. I'm not giving the definition here of Maufang loop, but you can find it even on Wikipedia. There is a condition, it's not any loop. So loop is like a group, but you forget about, I think, associativity. You still have a unit and you still have inversion, actual inversion. So every element H has an element H minus 1, such that H minus 1 is the unit element. So you forget, I think, only about associativity. But here you need something more, and something more which is satisfied in particular by unit octonion. So this is an example of this kind of structure. Are loops, but are loops satisfying satisfying some additional condition that I don't want to tell, but you just think about unit octonions. And okay,
Where loops in what sense?
It's called a loop. Group without
group without associativity is a loop, but a Maufang loop is something more. Still non-associative, but it's something more. But if you want, I can tell you later. It's, I have the definition here, just I don't want to waste time. Okay, so now we want to add topology to construct this convolution product. And of course, the only thing that we can do is working with this sum, the tolerance relation. And so assume that G and X now are topological spaces. Put on the image, on this R, the image of the canonical map, the correct topology, and here is the point. So you induce the topology, sorry. This is the canonical map. On G and X, I have a topology, and here, on the image of this map, I put the topology induced from this one. That will be some quotient topology if it is not injective. So with the correct topology, you can see that with this topology, that the relation is italic and only if G is discrete. This is really the only condition.
But why don't you topologize a full Cartesian square?
Because in general, this is true also for equivalence relations. Or if you, on the relation R, you put the relative topology from X cross X, then it will, usually that is not the topology that gives you an étale groupoid. There are simple examples, like a really square, I don't know, X is a closed segment, 0, 1. No, maybe no. Okay, I don't want to say something wrong. There is, again, even in our paper, there is an example where the relative topology from the Cartesian product is not the one giving you.
When you say relative, you mean this
subspace.
Subspace.
Yeah. Okay. So if G is discrete, R is étale, and that is the only case. So here you can play a little bit and construct examples, but I don't have an example to show because, I mean, you can construct this A3, this basic building block from this framework, but okay, it is a bit of an Docker construction. Still, here in principle, you have this canonical map, you can ask a lot of questions. If, I don't know, of Galois makes sense and give you something interesting, maybe the answer is no, but okay. So let me go on and talk still about the finite dimensional case. How much time do I have?
You still have 32 minutes.
Okay, yeah, it's a lot of time. I have 10 minutes for each slide.
Perfect.
Okay, so now I change point of view a little bit, and I want to connect this convolution product with this idea that you have spectral people and you truncate maybe the Hilbert space to kill the tail of the spectrum of the Dirac operator. So this idea of truncation. So in general, suppose you have a sister algebra B and a linear map T from B to B, call A the image of this linear map, then there is a naive way to put a product on A. You have two elements, small a and small b, in this image of T. You multiply them with the product in the sister algebra. The product will be in B, not in A, but then you apply T and you get something in A. So with this trick, you get a product on A, and the product in general, of course, will not be associative. So special cases when T is idempotent, meaning that T square is equal to T. And not only idempotent, but also completely positive contraction. And I'm not giving you the definition of this, but people studying these things know what it means. And otherwise, I mean, you can find the definition anywhere. So it is a standard, well, I don't know if standard, I mean, something that you find in textbook. It is known, I don't know if it's well known, but it is known that if T is idempotent and a completely positive contraction, then the product that you see here on top is associative. So this is just to say that this is not a completely crazy product, at least in the associative setting. There are people studying this product, and there are classes of maps T when this is associative and studying, interesting to study. Still, a still smaller class of truncations, let's say, of maps T is given by conditional expectations. So it is a conditional expectation if one of the following conditions is satisfied, they are equivalent 1 and 2. One is that T is idempotent and has norm 1, and the second is that T is positive, idempotent, and an A bimodule map. Any of these two conditions imply the other and imply that T is a completely positive contraction. So in particular, if you have idempotent and A bimodule map, you don't need to know what completely positive contraction means. You just need a positive. And okay, in particular, since they are equivalent, you have a conditional expectation is idempotent and completely positive contraction and give you an associative product. So this is still the case where you have an associative product. And a concrete class of example is when T is constructed from projections in B. Take any projection P in the sister algebra B, define T as the sandwich of an element in your sister algebra by P. Sandwich means P times X times P, where P is the bread and X the ham. And this is a conditional. Yeah, or yeah, for vegan, it's the vegan version, yes. And this is a conditional expectation. Okay, of course, here in this case, you can check actually by hand that you get an associative product. You don't need all this theory, but still, this is a class of examples.
May I ask a completely stupid question? I'm trying to imagine an idempotent with norm different from 1.
Well, this is not a projection. It's not that
it's not a
projection. Yeah.
Okay.
Okay. So this is a simple answer.
Yes, thank you so much.
Not
yes, I misread it.
Instead of studies.
Yeah. It writes idempotent, I read projection. Sorry.
Yeah. Okay. Now the next example, take as B continuous functions on the circle. Let n a positive integer, and then there are two obvious. There are two truncation maps that you can immediately think of. The first one takes a function, or in fact is Fourier series. Well, let's not say it's Fourier series because these are arbitrary continuous functions. So T1 takes a continuous function and gives you the Fourier partial sum, where you take the Fourier elements from minus n plus 1 to n minus 1. So this is the condition. You take finitely many of them. And T2, you don't see here the explicit expression, but it's just replacing the Fourier partial sum by this Cesaro sum. And then, the point is that these two maps, they have the same image. So if they use them to define a non-associative product, the image of this two map is the same for these two. And this is nice because T1 is idempotent but not positive. And this is something that we check very easily. And T2 is positive because you can write it as an integral with some positive kernel, let's say. And T2 is positive, but is not idempotent. So in both cases, these two conditions, at least one fails, and you can check that you don't get an associative product. And okay, so these I mentioned this because these are the kind of truncations that were studied both by me, Fedele, and Pierre when we were studying convergence of truncations in the sense of ordered unit spaces 10 years ago. And and also in more recent papers by many people, I would say Walter and others that okay. There are several papers on convergence from the point of view of truncations of the circle from the point of view of operator systems.
So the image is the same, but the product is different.
The image is the same, but the product is different, and also the two products have different properties. In these works about convergence, you don't care actually about the product. So, okay. So why I mentioned truncations? How are they related to tolerance relations? Well, if you have any finite simple graph, so any tolerance relation on a finite set, then the associated convolution algebra is a truncation in the sense that I explained before. So suppose you have a relation on X where X is the set 1n, 1 to n. So what is the truncation map? You can write down an explicit formula. So B, in this case, the big algebra is the full matrix algebra, and C here the field is complex number. So the B is the matrix, is the full matrix algebra. A is the image of T, where T is constructed in the following ways: just a sum. X is a matrix, is an n times n matrix. You multiply by the matrix EII from the left. This is these are the matrices in the of the canonical basis of
elementary matrices.
Yes, elementary matrices.
So these are projections
and matrix product. Elementary, yeah, and this is the matrix product. So on the left you have EII, on the right EJJ, and of course if you sum over all IJ, you get nothing interesting. But here you sum only over I and J that are in relation, and this is what kills insert zeros in your matrix. Then you can check that, okay, with this, in fact, the image is what you want under the identification of these elementary matrices with the delta functions, and the product defined by truncation and by convolution, they are the same. Now, this point of view, okay, gives you something more than just convolution algebra, because now you have a truncation of a matrix algebra. And in particular, you have so this T commutes with involution, and so what you get is a vector subspace of matrices that is closed under involution. It contains the unit. In the finite dimensional case, it is a unital algebra, and it contains the unit. So this is an operator system, and I'm not going to give you the abstract definition, not even the concrete definition in the infinite dimensional case, but in our case, this is what it is. So in particular, since you have an operator system, you can talk about states. You don't have to invent anything. You can talk about states in the sense of operator systems, which in this case just means what is a state of our convolution algebra in this sense is just something that you can obtain restricting a state of the full matrix algebra. Any linear map that you obtain by restriction of a state of B, this will be a state of A. So you have a surjective map from states of B to states of A, where A is the convolution algebra and B the full matrix algebra. This restriction, this surjective map is just a restriction of states. It's a surjective basically by construction. It's not always injective. So here again, the first thing, the first two questions that comes in mind is, okay, when is this injective? And the nice thing about finite dimensional algebra is you can do everything almost by hand. It's not really completely true, but you can check that this is injective if and only if. Well, first of all, if and only if it is injective when restricted to pure states. So you never have something that maybe on the worst state space is not injective, but on pure states is. You never have this kind of things. And unfortunately, this is also equivalent to 3, telling you that injectivity is only in the most trivial case when you have a full matrix algebra. So in particular, even if, yeah.
So you didn't give the there is a definition of states on operator systems. But
Well, here you can think just a restriction of a state of the matrix algebra.
so that is still the compact combination is still a state and pure state is still one points.
Yeah, so pure state are just a normal state coming from a unit vector and so on. Yeah. So, and here in particular, this projection is not injective, not even when the small algebra is associative, because you can have, even if you have a graph which is not connected, but with connected components that are complete graphs. So you have a non-trivial equivalence relation. Not only say not everything is equivalent to everything. If you have a non-trivial equivalence relation, A is an associative subalgebra, is a subalgebra of the matrix algebra, but still this projection of states is not injective. Okay, then you may wonder, okay, if I take a pure state, so a unit vector up to a face of the matrix algebra, when do I get by restriction a pure state of this tolerance algebra? And here you have some kind of result in terms of graphs. So first of all, if you have a unit vector v in c to the power n, you can define a relation that I denote by Rv as follows. I and j are in relation if and only if both the component E, well, Rv is a subset, is a subrelation of R, and if I and j are, say, tolerant to each other, they belong to this relation if and only if both the ith component and jth component of your vector is different from 0. This relation, if this sub-relation is connected, then we will say that this vector is R-tolerant. This is the name that we used. But so then, in fact, this is analogous. When you study proximity relations, something like this already appeared before in the paper by Kohn and Van Suilecom. This is what they called, so the associated state, they called it with epsilon connected support. And in fact, in the more recent paper, in the finite case, so not proximity relations, but arbitrary tolerance relation on a finite set, this thing is what they call R-connected. Okay, they didn't like R-tolerant, but as I said, I'm not good, and maybe neither the collaborators are good with catchy names. But in this slide, I stick with this name that is the same that is in our paper. So given a unit vector, yeah.
What are the main properties of the linear states? Is it linear functional?
For a sister algebra, these are unitary, so positive linear function. You apply it to the unit and you get one. For an operator system, still you have. I didn't tell you what is an operator system. So a concrete operator system is just a vector subspace of a sister algebra with these two properties. At least in the unital case, still stays send 1 to 1. In the non-unital case, I'm not an expert of operator systems. I don't know almost anything about it, especially non-unital. But so a class of operator system which is studied is one with approximate unit. And in general, I mean, you mimic the definition for sister algebras. You still have partial order. The real version that I know a little bit better. So the self-adjoint part of an operator system, at least in the unital case, is order unit space. And an order unit space is a real vector space with partial order and satisfying some suitable inequalities, let's say. There are some conditions on this partial order. Then you use the partial order and the unit, so order unit space because you have a unit, and you use these two to define states in the usual way.
Then what's the motivation for considered states?
Well, the motivation is that we have these truncations of sister algebras. We want to study convergence of these truncations and convergence from a metric point of view. Meaning that, at least for sister algebras or plus semi-norm satisfying some technical conditions, you can study convergence of, you have a metric on the state space. So if you have a sequence of these kind of sister algebras with semi-norms, you have a sequence of metric spaces and you can study convergence in the sense of Gromov-Hausdorff, for example. If instead of the sister algebra you truncate, you have something less, you have an operator system, you still may be interested in studying convergence from metric point of view, meaning convergence of state spaces with suitable metric. Okay, I mean, there are a lot of other reasons for introducing state operator systems, but this is what, I mean, in this framework, I'm very interested in. So anyway, so this is the definition of R-tolerant unit vector, and basically this is what gives you pure states. So a unit vector gives you a pure state in the usual way by sandwich, or gives you a pure state of the convolutional algebra if and only if it is R-tolerant. So there is some compatibility with this relation that must be satisfied. So you can completely characterize pure states of this convolutional algebra. So let me finish. This is the last slide, but
sorry, can you actually go back? What is a vector state exactly?
Okay, yeah. Well, for full matrix algebra, every state is a normal state, meaning that it comes from sandwich with a unit vector. You have a V star multiplied by the matrix, and then V in column. So you take the average on this vector of your matrix, and this is a state.
Okay, that's.
I mean, I say vector state just to mean the state that you get from this unit vector in the standard way by taking the inner product of V with a matrix.
Okay, yeah.
It's just to have everything in one line. I don't know if a vector state is really a name. It's just to have everything in one line. So it's the normal state associated to this vector or to the corresponding rank
using
one.
inner product. That's what I would use.
So, okay, so now last slide is about the positivity, because the point is that you use positivity to define states. These are, they should send positive elements to positive elements. Even in the case of a non-associative star algebra, you have a natural notion of positivity involving the product, but we did not use the product to define states. So states of this structure of operator system is it apparently doesn't talk to this algebraic structure. So how are these states related to this to the notion of positivity that you would get from the convolution product? This is what I would like to try to explain in one slide. So as before, you have your convolution algebra, which is inside n times n matrices. You have this capital T, which is your truncation map, and given a matrix A in your convolution algebra, I will write that A is greater or equal than 0 with this sign if it is positive in the standard sense, so positive semi-definite matrix, and I will say that it's greater or equal than 0 with this different symbol if it is the image via T of some positive semi-definite matrix. So in the second case, there is a positive semi-definite matrix B such that A is T of B.
Sorry, very stupid question. Again, what is semi-definite?
Because it could be 0, it's not strictly positive.
Ah.
So positivity for C-star algebra is not really positive. 0 is positive in the sense of C-star algebra. So, okay. Yeah, see, in our case, T has an explicit form, and in particular, it is idempotent, which means since it's idempotent, if A is positive in the first sense, since A is equal to T of A, then it's positive also in the second sense. So T is an idempotent map in our example. So the standard notion of positivity implies the positivity coming from truncation. Still, there is no product. So, well, since we have a star algebra, a natural way to define positive elements would be to say, okay, an element A is positive if I can write it as a sum of some bk times bk star, where all these elements bk are also in this algebra A. I mean, this is what this is one possible notion of positivity versus star algebras, and in that case, you don't even need the sum, right? you just one element is enough. Well, so in principle, this would give a third notion of positivity, but I don't want to introduce it as a symbol. But first of all, we can observe that also this, if A is of this form, then it is positive in the second sense. In this sense here, this is true. So how are this positivity and this kind of decomposition related? They are not equivalent. So not every A that is positive in this sense can be written like this. And this happens, these seconds, let's say second and third notion of positivity, they happen, they are the same if and only if the graph satisfies a suitable condition. If and only if each connected component has a dominant vertex, meaning this is a vertex that is connected to everything else, to every other vertex of that connected component. So this is necessarily a sufficient condition for these two positivities to be the same. So in particular, if this is satisfied, the second notion of positivity.
Sorry, when I say connected to every other, I mean directly connected.
Directly, yeah, sorry, yeah, connected by an edge. Yeah. Okay. Now, still, can you reverse this arrow, how these two are related? So let's say that the second one is the one which is in some sense, at least for a class of relation, is the one that comes from the product. So can you reverse this arrow? No, of course, no. And how are these two related? This is explained in the next 3 lines. So you can, in the standard way, you can transform elements of matrices into linear maps using the trace. So phi of x, if x is a matrix, phi of x is the map given by trace of x star, and here you insert your argument. This not only maps, of course, matrices into dual of matrices, into linear maps, but also maps this subspace A to its linear dual. And in particular, when you restrict it to this subspace A, it maps the second positive, the second partial order to the first one. And it is in fact an isomorphism of ordered vector spaces. So this is, there is some kind of duality. And in particular, using this kind of duality, now you can characterize states using the second partial order. Under this duality, now a state is just an element of A, which is positive in the second sense and with trace 1, like you would do with density matrices.
Sorry to stop you again, but yeah, I'm having problems imagining why it is true. I'm wondering about this implication that I have something positive. So why does it have to be in the image of a positive other matrix under T?
So sorry, can you repeat?
I'm wondering if there's implications. I take A, which is positive, right? And we have this implication. Yeah. So this means that there exists a positive matrix such that T of this matrix is my A.
You take B equal to A. A is equal to T of A for any A in the image of T, because T is idempotent, right?
Wait, so A is...
like capital A is the image of T.
Ah, okay.
So element here in the image of T. So if you apply T again, you do nothing. It's something very elementary.
I was missing this, that is in the image of T. Okay, okay.
So that's nice. Okay, so thank you very much. And we can move to questions.
Let's thank our speaker. Thank you so much. Okay, guys, we have plenty of time for questions.
So maybe I remove the full screen.
And I see that there is first question from Warsaw. Tomek, go ahead.
I have several questions. So first, my first question is following. Assume that we have this relation. Can I write on whiteboard? Yes. Can you see this?
Yes.
Yeah.
Okay.
R.
So
I'll put it full screen.
Please
maybe,
do, yes.
You have more.
Okay. So for every relation, you can form a coequalizer in this diagram, okay? So it's like a quotient. My question is, if you form your convolution algebra of this relation, is it true that, or what are conditions under which this is equivalence relation with respect to Morita equivalence.
Yeah, so yeah, this is a very interesting question. We were wondering about something like this. So the problem here is that to define Morita equivalence, you use bimodules. And for a non-associative algebra, bimodules, first of all, means that multiplication from the left and from the right should commute. So you have some kind of associativity. But even here is not even clear what is a module for this kind of non-associative algebra. So
what about magma-like module definition?
Yeah, probably something like that could work, but we didn't try. I don't have an answer. We were thinking about it. Of course, once you know what is a good notion of module and of a bimodule, still there is a lot of technicality. Then what is a notion of Morita equivalence? When it's this bimodule full and so on. But yeah, I was thinking about it, but I have no answer. Yeah.
For a topological space, these two constructions make sense.
Yes.
Okay, so let me erase this one. Second one, if we have a relation R, we can take its transitive closure, okay? And then you have your convolution algebra of this relation, A of R, and you can have this A of this transitive closure of this relation.
Yeah.
And the right-hand side is an associative vector algebra. Okay.
Yes.
Is there some relation between these two? For instance, a map.
Yes.
Map.
In the, you can see with counterexamples in the finite dimensional case. So in general, more generally, you can ask, maybe I have a relation and a sub-relation. Are the algebras related? And I don't see, in the case for our construction, the only thing that you can say that the algebra on the left in your picture, the one on the left is a truncation of the one on the right, which is not very interesting because both are truncation of matrices, but it is not a subalgebra. And you have an injection, an injective linear map, but you don't have subalgebra or anything.
Okay, but is this A of R in the finite case?
Yeah.
Embedding into matrix algebras?
Yes.
Isn't of this form?
Sorry, what is the question?
Is the embedding of this convolution algebra of your relation to matrices?
Yeah, so you have
it of this form?
Yeah, so suppose you have a relation like this, R trans, and the sub-relation, they both are embedded into matrices, and one embedding factors to the other. So,
so you have it.
I think this should be true because you have
Okay,
you have an explicit form, at least in the finite dimensional case, it should be easy to check. So I would bet that is yes, the answer. You immediately check probably.
So at least there's some relation to associative vector algebras.
What do you mean? Sorry.
So you are using this embedding into associative algebra in many places.
Yeah.
Defining positivity and so on and so forth. So maybe it's a general mechanism of embedding of the convolution algebra into this associative one. Well,
this kind of construction of truncation you can always do for any sister algebra. And now, we studied the finite dimensional case because basically the convolution product, if you have a relation which is étale, if it is not on a finite set, it's very close. So you can imagine maybe, I don't know, something countable acting, not really acting, almost acting on a set. But if you don't have finite, maybe you have countable, but not much more. So at least if we consider so only et al. And this product with a sum instead of integral, yeah, you can find more example. The one which is not finite dimensional is the non-commutative torus, which is of course associative, but still it comes from an et al. You can get it from an et al. Equivalence relation, where, or from the action of zeta, which is discrete but not finite. But that is a specific example.
Okay.
I don't know if you can get a much more discrete but not finite dimensional non-associative case. And in the non-discrete case, the problem is that, okay, for a groupoid, you know what is a R system, but here you don't have a groupoid. So you can try to mimic this relation that you have, the definition that you have for groupoids. But for groupoid, somebody else took care of the whole theory, the technical part, properties of R systems and so on, existence of product. So it could be very difficult to generalize.
Okay. So the last question, still about the relation between your convolution algebras, non-associative ones and associative ones. I forgot the name of this tolerance relation when the distance between 2 points is bounded by epsilon.
Yeah, proximity relation.
Yes.
Proximity. Oh, okay. Thank you very much. Proximity. So about this proximity, if you could give me some white room on this
Of the slide, which is as empty.
Empty slide.
I wanted to go,
Yes, I want to.
or maybe last.
Yeah, but you can just.
Write something.
Yeah.
Yeah.
Oh, very good. Very good. Thank you. Okay, so we can speak about a family, about families of proximities. Okay, so this means that we have, let's say, trivial bundle like this over the interval 0 epsilon, and then we have families of points. Then between such points, generalized points, let's say, sections, we can define this relation that x is, let's say, in the relation with y if d of xy is smaller than, and now, since they are in fact functions of epsilon, I can write, for instance, O of epsilon.
But you mean not epsilon? Epsilon is fixed, right? Maybe the value is 1.
Yeah. So t, let's say t. Okay.
Yeah, where t is in this interval. Okay.
Yes. Okay.
Yeah.
And then so this is very similar to this proximity, but proximity in the family.
Yeah.
For proximity in the family, you have transitivity, because some of expressions of type O capital of T is of the same type. You cannot do this with a single epsilon, because if you use the triangle inequality, you obtain epsilon plus epsilon, so 2 epsilon, which is different from epsilon. But for O of T, you obtain transitivity of this, and this is transitive relation. And you can form a convolution algebra for such things, and you obtain a continuous field of sister algebras over this interval 0 epsilon. Okay.
Yeah.
But in this family, you can speak about proximity in the sense you cited. Okay. Yeah. So you have this convolution algebra over these, and you have fiber-wise these algebras, these convolution algebras of this relation given by a fixed t.
Okay.
Okay. So this is again something like relationship between some associative convolution algebra and this non-associative one.
Yeah.
Okay. What would be the meaning of this?
Well, I mean, it is an interesting question, but I never thought about it, so I have to think about it. Maybe I can tell you next time. I have to
Okay,
think.
so you.
So
So,
let's say, but
so my motive of my all questions was that there are many ways of relating your convolutional algebras with associative algebras, and I have many questions about what is happening there.
In the case of proximity relation, we didn't do it, but I mean, there are many interesting examples where the proximity relation is transitive. For example, when you have an ultrametric, like I don't know.
Yeah, so this is mimicking ultrametric. If you think instead of O of t, you mean, for instance, modulo t squared.
Yeah, but so when you take, I think, a p-adic number with the p-adic distance, that is
precise. Yes.
Proximity relation is transitive, and you could try to see what is the convolution algebra, which is associative in this case, or maybe the other.
Yes, but the problem with this ultrametric and this p-adic case is that here what I wrote can be evaluated at epsilon.
Yeah.
In ultrametric, this formal parameter or prime number cannot be made a number, a real number.
Yeah. Well, I don't know. In any case, one should try and see what he gets. I think.
Okay, so thank you very much. It was very inspiring.
Adam, you are next in line.
Thank you.
Adam?
I cannot be right.
Yes, so maybe one question. So you mentioned this unit sphere in octonions, and this is something like a 7-dimensional sphere. So is there any reason behind this fact that this bundle for this 7 sphere is trivial and some connection with this existence of octonions?
So sorry, I didn't get one word. What is trivial?
The bundle, the tangent bundle for the 7-dimensional sphere is trivial, yes?
Yeah.
And is there any connection between this fact and the fact that there is a construction of octonions?
No, I mean, I can check. I'm embarrassed because I didn't check again what is the definition of Mopang loop, but it's something algebraic. I mean, the fact that unit octonions form this kind of loop comes from the fact that, I mean, they are units in some kind of division algebra. So it's something algebraic, not geometric. I would say that the parallelizability has nothing to do with
size.
It's more algebraic stuff, yeah. But
it's topological. If I could answer this question, it's a classical problem of topology solved by means of K-theory by Adams about parallelizability of spheres.
Yeah.
And this is related with division algebras. Octonions is non-associative division algebra.
So it works like for Lie groups.
Denions, I don't know.
The tangent space. You can move it around the tangent space, like in the case of a group. If this is what you're saying.
There is, in fact, there is some connection, yes?
Yes.
Yeah.
Okay.
So, Gianni,
there is a Lie algebra relation in this. I mean, the vectors to the left do not form a Lie algebra. Because this is actually, there is a rational loop for the Lie algebra. So it's related to what Adam is saying via the Lie algebra.
Yeah.
Adam, you heard it?
Not quite, just barely.
You can speak up.
Okay,
maybe
S7 is parallelizable. So if there exists 7 vector fields which are globally defined, it's not closed Lie algebra because S7 is not a group.
Yes.
And so in this expression of it's only a loop.
So if you take a global frame for the tangent bundle instead of a Lie algebra, what you get is the analog of Lie algebras for Mopang loop. This was the comment.
Okay, thank you.
All right, anybody else? Anybody from Trieste? No questions from Trieste? Okay, so anybody else on Zoom? No, it seems we cannot, we will not tolerate any more questions. So in this case, let us thank Francesco again. Yeah, thank you so much. And let me remind you that next week we have a speaker from Buffalo, New York, Alexandro Kilvasito. We'll still host it here in CISA, but the speaker will not be here. So I think it's stop recording. Francesco, we stop recording.
Oh, basta.